Okay, welcome to week 2, part 2.
We have looked at four different kinds of options so far, namely European calls and puts and American calls and puts. The distinction between those is in the ability to exercise early in the case of the American options. Now, we've looked at three different methods for pricing options. In the case of the European call and put, we can use the closed form Black-Scholes-Merton formula, which is very quick to compute and very convenient. But unfortunately, that's not available for the American options. We also looked at using a binomial tree as a means of computing values of options, and that will work for both European options and American options. Finally, we looked at using simulation to price European options. Now, for American options, it turns out using simulation is not so straightforward because of the ability to do early exercise. This is one of the very important things that Professor Lahosky will discuss with you during the simulation course that he teaches. As another example of using simulation to price options, I'm going to introduce here what are called Asian options. Asian options are an example of what are called path-dependent options. That is, a characteristic of the European options and the American options is that we only needed to look at the underlying stock price at the exercise time, either the final time in the case of a European call, or possibly some early time in the case of the American call, an American put. But for the Asian call, and for that matter for the Asian put, we actually care about the mean value of the stock price over some period of time. So the value of an Asian call on a stock is actually going to depend not just on the final time value of that stock, but actually on all of the intervening stock prices up to and including that expiration time. There are variations on how Asian options are defined. We're going to be talking about the arithmetic mean version of the Asian call. That is, we're computing the arithmetic mean of the stock prices over time. As a side note, I want to mention something. You may be wondering about these names for things: European call, American call, Asian call. Does that mean that in Europe, calls are set up in the European style? In America, they're set up in the American style? In Asia, they're set up in this Asian style? No, actually, these names are sort of a historical joke in a way, and I will leave it to your other professors to tell you the various stories about where these names came from. So they're really just arbitrary labels, and we could have just as well called these things, I don't know, buffalo calls and giraffe calls and lion calls. There's nothing European or American or Asian about these formulas for producing these calls.
If you look back at the previous lecture,
when we used simulation to compute a price for a European call, all we had to simulate was final time stock prices. We didn't really care about the paths for how we got to those final time stock prices. We just used the Black-Scholes-Merton model combined with random draws from a standard normal distribution to compute a distribution of final stock prices. And using those final stock prices and the final time payoff formula, that is the maximum of either the final time stock price minus the strike or 0 if the stock price at the final time was below the strike. All right, we used that final time payoff, and we were able to roll that back then using the interest rate to get a current time call price based on the average of those simulations. Now, for Asian calls, we're more or less doing the same thing. We're drawing random values from a standard normal distribution, but now we have to simulate entire paths of stock prices, not just final time stock prices. And what this means is that it's going to take significantly more resources, significantly more draws from the standard normal distribution in order to get simulation done for an Asian option. Okay? We're going to specify the number of times that the stock price has to be evaluated. For example, we're not going to try to compute the mean of the stock price at every second of every day up until the final time. We are going to, for example, specify that the trading day closing price is what we're going to use in our computation of the mean stock price over the time interval. All right, so that's not an infinite number of stock price observations, but it's still a fairly large number. So, how are we going to do this? Well, it turns out that because of weekends and holidays, there are 252 trading days in a year, more or less. Some years there's 251, some years there might be 253 due to a leap year. But on average, there are 21 trading days per month. And if we want to use the same 5-month time period for our Asian call, as we have used in our examples for the European call and the American call, what that means is that we're going to need to keep track of, or we're going to need to simulate and then record stock prices for 105 days between the initial time and the final time. Now, remember that from the Black-Scholes-Merton assumptions, we can generate samples of final time stock prices using this formula where we draw a value from the standard normal distribution in order to compute that final time stock price. Okay, so for each draw that we do from a standard normal distribution, that gives us one possible final time stock price following the assumption of the log normal distribution under the Black-Scholes-Merton model. All right, well, we can generalize this formula by just assuming that the final time is some small time step. So let's suppose that we are currently at some time little t, and we want to move forward by some small time step delta t. Then the stock price at time t plus delta t is simply that same formula where we just replace capital T with delta t, okay? So if we are currently at a stock price of S sub t, then we can simulate the stock price at S sub t plus delta t by drawing from a standard normal distribution and applying this formula. Our computations are all on an annualized basis. That is, we've got the annual interest rate here, and we've got the annual volatility of the stock. So we need to convert delta t into years. 105 trading days is equivalent to 4.167 years, that is 5 months, and consequently one trading day, which is our delta t, is going to be 0.003968 years. All right, now if we start plugging this into code, first I'm just going to show you one example stock price path from simulation. We're going to be using NumPy to obtain our random values and to store our stock prices and call values. I'm also going to be using Matplotlib's PyPlot in order to display the path, or later the paths, that we're going to be drawing. Here we have the parameters of our contract. Well, the current stock price is not really a parameter of the contract, it's just an observation. So we're going to use the same setup that we've used for our previous calls and put. We're going to assume that the current stock price is 50, that the strike price is also 50, that we've got a 10% annual interest rate, the volatility is 0.4, and as we've seen, we are going to have 105 trading days, and each one of those trading days is this value that we computed. I'm going to initialize NumPy's random facility seed to 0, so that if you try this out, you'll see the same results that I do. Of course, that's optional. You can leave that out, and you will still get a valid simulation. It just won't be identical to the simulation that I'm going to do. Okay, so now we need to draw our z sub i's. That is, our draws from the standard normal distribution, one draw for each day for which we're going to simulate the evolving stock price. The price path for the stock is going to contain t days plus 1 cells, because the first day, the first recorded stock price is just S sub 0, and then we're going to have the stock price evolving over 105 subsequent days. Here's our initialization of price path sub 0 to just S sub 0. And then we're going to roll forward using our random draws from z sub I and applying our formula as shown on slide 5 here to compute simulated price paths going forward for subsequent days. When we're all done with that, we're going to compute the mean of the stock prices over the 105 days following today. And I'm also going to display a plot showing the stock price on each trading day. So here's what our plot looks like. And interestingly, this particular simulated stock path is pretty volatile. It shoots way up to above 70 in just about a month, and then drops back down to almost as low as 45, around 83 days, and then comes back up to closer to the original price. Well, I guess it gets up to about 57 on the final day. So that's a pretty volatile path, but, you know, such things happen. And notice that the mean stock price that we have over this over these 105 trading days is 58.17. We're going to repeat the same thing for 20 days just so that you can get a better understanding or a better feel for what the distribution of these paths is going to look like. Okay, so once again, we have our usual setup here, but this time we have 20 paths instead of just one. And so instead of, let me contrast this with our one path code. Okay, so instead of just drawing one draw from the standard normal distribution for each day, now we have to draw 20 paths for each day. So we're going to end up with a matrix here with 20 rows and 105 columns of draws from a standard normal distribution. I'm setting up my price paths here to be initially 0. Each row is going to correspond to a path, and each column will be a day within that path. Here I'm doing a vectorized assignment so that the initial column of every row is going to get the initial stock price of 50. And then for each trading day, I can also do another vectorized assignment here, a vectorized computation, in which we're computing the simulated stock prices for each subsequent day based on the previous day. And right here is where we're grabbing values out of our column of random draws from the standard normal distribution. Okay, and then we're going to plot what's going on here. So let me show that plot. Okay, so there we have that plot. And if you follow along most of these paths, they're not quite so volatile as that first path that we looked at. All right, let me just run these things interactively so that we can see what's going on here. I've actually got this code available in program files that you can look at. So here is the code for just creating one stock price path. We're importing our modules, we're setting up our parameters, initializing our seed, and then we're computing 105 days worth of stock prices with the initial stock price being S sub 0. So let me run this thing, F5, and there we are. So there we have our plot of one simulated 105-day path for stock prices. Now let me run the 20-day version. Okay, so, I'm sorry, not 20-day version, 20-path version. So this is the 20-path stock price simulation. Same parameters, except this time we've also added n paths because that's the number of paths that we want to create. We're initializing the entire first column of our price paths to be S sub 0, 50. And then we're rolling forward, computing the subsequent columns based on the changes in the stock price from the current column stock price. And then displaying this plot. Okay, so there we go. There's 20 paths. Now, 20 paths is not nearly enough to get us a good estimate for the Asian call price. We need to probably have thousands, if not tens of thousands or hundreds of thousands of paths in order to get a precise enough value for our Asian call price. So let's take a look at what's going on with that code. Okay. All right, so each path is just one sample from some number n of different paths. And the call price that we're going to compute from each path, C sub I for the ith path, is going to be the payoff function discounted back to the current time. So, in other words, the mean of the daily closing prices minus the strike price, the maximum of either that or 0, discounted back. Now, if we have, we have n of these things, and so we can compute C bar sub n, the mean of all of those call prices, and we can also compute the standard error of that mean by computing the standard deviation of the over all the call price paths and dividing that by the square root of the number of paths that we have simulated, okay? So once we have that standard error, the 95% confidence interval around the mean of the call prices is going to be plus or minus 1.96 times the standard error. If n is small, that's going to be wide, and the larger n gets, the narrower that will get. So we can choose a sufficiently large n in order to satisfy, at least in theory, any confidence interval that we would like. Now I say in theory because in practice on your computer, if you choose an n that's too large, you may not be able to allocate enough memory to actually do the simulation. All right, so how do we get an n that we want? And in our case, we're going to get an n. We're going to try to get an n that will give us a confidence interval of half a penny. All right, so plus or minus half a penny around our call price. Well, since we don't know n to begin with, let's just pick a reasonably large n. 10,000 may not seem very large when you're dealing with n's in the millions, but still, n of 10,000 is pretty large. And that will give us not only a mean for the call prices, but it will also give us a standard deviation for the call prices. Now, that standard deviation that we get for a certain simulated set of call prices is an estimate of the true standard deviation of the distribution of all such call prices for all such possible paths from our simulation. Therefore, as n gets larger and larger, we can assume that our estimated value for the standard deviation of that distribution is going to remain pretty much the same. And consequently, we can get a better n, a bigger n, using our initial estimate of what the standard deviation of that distribution is. So let's walk through the program that first uses a sample size of 10,000 to do an initial simulation to get an initial mean value for the call price and, in some sense, more importantly, an initial estimate for what the standard deviation of those call prices is. We'll then take that initial estimate of the standard deviation and use that to select a better n that will get us to our plus or minus half a penny confidence interval. All right, so here's that code. Now, we had previously, let me flip back to the previous code that we looked at for plotting these paths, okay? We had previously created an array, a two-dimensional ND array, of draws from the standard normal distribution. Each row was a path. Each column was a number of days for, or was a particular day in our sequence of trading days. Using that two-dimensional array of random draws, we then applied our Black-Scholes-derived formula to compute the simulated price paths. In this code, we then just plotted what those price paths, but now in our code here, after we have computed all these price paths based on the ZI that we draw for some number of paths, we're going to get ourselves the call prices associated with each one of those paths by using our discounted payoff. Okay? So we're going to compute the mean of all of the trading days for each path, for each column, starting from the sub 1 column, because the sub 0 column is just the initial stock price. Because price paths here is a two-dimensional ND array, and we're trying to compute the mean of one of those dimensions, we have to actually tell that the NumPy mean function that we want to compute these means over rows, not over columns. Okay? Otherwise, we would end up getting the mean for all of the paths over individual days. What we want is the mean over all of the days for individual paths. So we will get back an ND array containing the n discounted payoffs from those n paths. In this case, this is actually an argument called n paths. And we've wrapped this code in a function named simulated CI so that we can call this function over and over again for different numbers of paths. We'll return that vector of CI values, that vector of call values, when this function is done. Okay, so notice that we pass in the initial stock price, the strike price, the interest rate, the volatility of the stock price, the total number of days in each path, the length in years of each day, and the total number of simulated paths that we want to create. And then this code does the same thing that we did for simulating the paths, except instead of displaying a graph of the or an image of the simulated paths, we take each one of the average stock prices for the paths and compute and return a vector of these call prices. All right. So next up, once we've got that function defined that we can call, we're going to start, as we described, by setting n to 10,000 and seeing what vector of call prices we get from simulation, as well as what the mean of those call prices is. We're going to compute the standard deviation of those call prices from simulation and get the standard error by dividing by the square root of the number of paths. Now, it could be, we could be lucky, and it could be that this confidence interval that we get from setting n to 10,000 is within plus or minus half a penny. It's very unlikely, but that could happen. But let's assume in real life that we're not that lucky, that the confidence interval is too wide, and we need to pick a better value for n. Okay, so what we can do is, if the confidence interval is too wide, we want to select a better value for m. Let's assume that the standard deviation we're going to compute from our second simulation of call prices, all right, we're going to call this CI2 for our second simulation of call prices. The standard deviation of that ought to be very close to the standard deviation that we already got now for our initial simulation involving 10,000 paths. So if we want to get a confidence interval that's only a half a penny wide, plus or minus half a penny, we know that we can compute that by 1.96 times the standard deviation of the CI2 divided by square root of n2. But we haven't done the simulation yet, so we don't know CI2. We're just going to assume that we can plug in the standard deviation for the original CI in place of the standard deviation for CI2 and divide by square root of n2 to get ourselves 0.005. Well, we're actually looking for n2. We've specified this precision 0.005. We're actually looking for n2, so we need to multiply by the square root of n2, divide by 0.005, and then square, and that will get us an n2 that is more likely to get us the narrow confidence interval that we want. Now, I want to be clear that we are not engaged in trying to optimize what the perfect n2 is. We're just trying to find a good enough n2 so that we get a narrow enough confidence interval and that the simulation time is not outrageously long. So we're not going to run simulations over and over and over and over and over again until we find exactly the correct n that will give us exactly as close to 0.005 confidence interval as we can get. We just want a good enough n to work. It's possible that this value for n is maybe going to give us a confidence interval that's just a little bit too wide. So just to be safe, let's throw in a fudge factor here. We'll multiply it by 1.5, and we'll assume that, okay, this approximate value for n times 1.5, surely that will be big enough to give us a narrow enough confidence interval. Here's the code making use of that computation. Now, in addition to doing this computation, because we have division and multiplication by 1.5 in here, that will result in a float, and we can't use a float as the number of simulations we want to do, so we're going to convert that value to an int, and we'll then display what that new and improved n is, what the value for n2 is. We'll run another simulation, this time using n2 as the number of paths. We'll compute our mean of the returned vector of call prices. We're going to call that C2 bar. And we'll get ourselves the standard deviation of the CI2 and use the square root of n2 to compute the standard error for simulation number 2, for the second simulation of n2 paths. Then we finally get our confidence interval, and, well, I'm cheating because I've already tested this and I know it works, but we're going to assume now, or we believe we believe that this confidence interval is going to be narrower than plus or minus half a cent. All right, so let's prove that that's true. I'm going to run this application. Let me pull it up. This is our Asian call sim price. And first we import NumPy. Then we define our function that will create a simulation for some number of paths of stock prices. We set up our parameters. The initial stock price is 50. The strike price is 50. Interest rate is 10%. Volatility of the stock is 40%. The number of trading days is 105. The length of each day in years is 0.003968. And we're going to start with an N of 10,000. By the way, in case you have forgotten a little detail from a few weeks ago, remember that you can, if you want, put two statements on a single line by separating the two statements from each other with a semicolon. All right, so I was just a little tight for space on my slide, which is why I did two variable creations on each line for these 6 parameter variables. All right, so we're then going to do our simulation involving 10,000 paths. It's very unlikely that we will get a tight enough confidence interval there. In fact, I know that we won't. So we're going to use the standard deviation that we computed from that initial simulation to get ourselves a better N2, which is going to involve this fudge factor. We're going to multiply whatever we get by 1.5. And then we'll do our second round of simulation using N2 paths rather than N paths, and see if our confidence interval is in fact within plus or minus half a penny. Cool. So let's run this. We're going to run it. All right. So there we have our call price for 10,000 paths. And from that and from the standard deviation, we compute that we need a little over 6 million paths to get the narrow confidence interval that we want. this first confidence interval for n equal to 10,000 is pathetic. We're plus or minus 10 cents on this price for the Asian call. Now, I've been babbling away for a bit here, and this simulation is still running. So as you can see, this is taking some time. Why is that? Well, the value that we got for N2, remember, is 6 million and something. Recall that there are 100 days, 105 days in each one of these paths. So we're not just simulating 6 million values, we're producing 600 million values, more than 600 million values from simulation, and that just does take quite a long time. Eventually, we get a result, 3.449, and yay, we did get a confidence interval that is tighter than half a penny. Okay, so we did better than plus or minus 0.005. Now, you can find online tools that will compute Asian call prices for you, and I found an easy-to-use Asian pricing tool at, well, I don't know how to pronounce this, cogit.com/free tools. And if you type in the parameters that we're using for specifying this this Asian call with 105 trading periods of the 0.003 whatever years for each trading period, initial price of 50, strike price of 50, etc., it computes a value of 3.45. So we're good. We got the same value. We got the same value as one online tool. Now, we may find other online tools that we don't match with, but we can be pretty well satisfied that we got the right answer. Okie doke. All right, and so we're doing more than 6 million paths, and we're doing more than 100 simulated stock prices per path. So this is more than 600 million individual simulated values that we're computing, and that does take a very long time. So how can we improve the time now that we've achieved the confidence interval that we want? Well, to get the confidence interval that we want, ideally we want our standard error to be small. And we, in the examples that I've talked about, have been concentrating on finding an appropriate n so that we can decrease the standard error to get to the confidence interval precision that we want. All right, so increasing n is one way of decreasing the standard error. But there's another very important way of decreasing the standard error, and that is to decrease the standard deviation of the simulated prices. And this is something that you will see in glorious, critically important detail in Professor Lahosky's simulation course. Not only is it possible to increase n in order to reduce your standard error, but there are also various techniques for reducing the variance and decreasing your standard error in that way. So that will allow you to do fewer simulations and still achieve the narrow confidence interval that you want. All right, so this is a preview of coming attractions.